Hi guys, welcome to another video where we take a look at another interesting problem in mathematics, where we can have a look at how the problem solving process works when it comes to figuring out the solutions to non-routine problems. So the problem that I've chosen for this particular video is from this book, Challenging Problems in Geometry, by Alfred Posamentier and Charles Salkind. So I've used one of these two authors have another book, Challenging Problems in Algebra, which I've used in some other videos. This is another book in their series, Challenging Problems in Geometry. Highly recommended for GCSE A-level maths students who really want to give themselves a challenge. This book scares me sometimes because some of the problems in it are really, really difficult and challenging. And I'd be lying if I said that I've managed to solve all of the problems in this book. Some of them are really genuinely challenging problems. So we're going to take a look at one of them from chapter 4, problem number 11. So the chapter is called Circles Revisited. And the problem that we've been given is, the information that we've been given, or the data is that two parallel tangents to circle O meet the circle at points M and N. A third tangent to circle O at point P meets the other two tangents at points K and L. Prove that a circle whose diameter is the line segment KL passes through O, the center of the original circle. So the diameter of the new circle has endpoints K and L. So if I were to draw a diagram to represent this situation, it might look something like the following. So we've got our circle, and we've got two parallel tangents. So I'll try to draw them the best that I can. Doesn't matter if they're a bit wobbly. So that's M and that's N. And then we've got a third tangent, which I'll try to draw in. Again, it's going to be a bit wobbly and it doesn't even look like a tangent. It doesn't make any difference though. And that intersects at P. And then we've got, so it intersects the circle at the point P, even though it doesn't look like it from my diagram. It's a bit crap. And intersects the other two tangents at the points K and L respectively. By the way, there is also a follow-up part to this problem which we're going to take a look at, but I'll come on to that once we've done the first parts of this problem. So I had a couple of possible ideas about how I was going to go about this. So what I need to show is that if I have a circle now whose diameter is KL, then it will pass through here, the center of the original circle. So this will be a point on the circumference of my new circle. So one of the things that I was thinking about doing here was I wanted to show that if let's say we've got the point A here, which is the midpoint of KL, then if I can show that the distance from A to O is the same as the distance from O to K and from O to L, that would mean that these are all radii of the new circle. Again, based on the diagram, which is not particularly well drawn, it doesn't look like that's going to be the case. But remember, when we draw diagrams to help us solve problems, we're not looking for accurate diagrams. We don't need accurate diagrams. We just need diagrams that are going to point us in the right direction. So I've got an idea. It's kind of represented to a certain extent in this diagram, but ultimately I can't, even if I did have a really good accurate diagram, I still can't make inferences directly from the diagram. The diagram is an aid to me, but it's never something that I can look at and say, and just draw inferences directly from it. I still have to go through the logic to solve the problem. So I might see something in the diagram, a pattern, some kind of relationship, but I can't say because I see that in the diagram, or I think I see that in the diagram, or it looks like that is in the diagram, therefore it must be. I can say, okay, I think I see this pattern in the diagram, this relationship or whatever, and now I've got to do the algebra, I've got to do the, I've got to go through the logic, the rational thought, which mathematics depends on to arrive at my solution. I have to prove rationally that that pattern is actually there. So typically using maybe algebraic techniques and things like that. Okay, so that was my original idea for this. But this, I couldn't really make any progress with this, unfortunately. And it turns out that that's not really the best way to go. An alternative idea that I had was to try to show that the angle here, KOL, is a right angle. So if angle KOL is a right angle, then KOL is kind of a semicircle. Remember, the angle in a semicircle is a right angle, and that's an if and only if theorem. So if KOL is a right angle, then KOL is a semicircle, let's say. It's not necessarily very clearly worded, but that's the idea that I had. That expresses the idea that I've got, that if I can show that KOL is a right angle, then I can draw a semicircle through KOL, and therefore I can complete the circle, and KL will be a diameter of that circle. Or maybe I could have worded it by saying that KL is diameter of a semicircle. However, whatever, this just represents the idea that I had, irrespective of how carefully or how clumsily it's worded. So, how can I do this? Well, what I can do is I can form a cyclic quadrilateral in the following way. By drawing a line, remember M and N are going to be diametrically opposite because these are parallel tangents. This is going to be a straight line from M to N. It's going to go through O to N. Okay, so remember that the angles, opposite angles in a cyclic quadrilateral, sorry, it's not a cyclic quadrilateral, it's just a quadrilateral. But angles in a quadrilateral add up to 2 pi or to 4 right angles. Okay, so angle KMO plus angle LNO are going to be equal to 2 right angles. This and this. OM is a radius and it meets a tangent at M, therefore they meet at right angles. And similarly for ON and the tangent through N. Okay, so that means that angle MKP plus angle NLP must be equal to also 2 right angles. So just to clarify, this is not a cyclic quadrilateral. I don't know why I said cyclic quadrilateral. It's not a cyclic quadrilateral at all, but it is a quadrilateral. So we're talking about the quadrilateral KMNL, just for clarity. So the 2 angles here are right angles. Therefore, the remaining 2 angles here and here must also add to two right angles, so that the total sum of all of the interior angles of this quadrilateral are going to be 4 right angles. Okay, but notice that because we've got a line here from L to O, that is going to bisect this angle here. Why is that? Because if I draw a line from O to P here, where this third tangent contacts the circle, the triangles OLP and OLN are going to be congruent, because OP is a radius, ON is a radius, so they're the same length. OL is common to both of the triangles, and they've both got a right angle. So the hypotenuse of each triangle is the same length. They've both got a right angle, and they've both got another side of equal length, and therefore they must be congruent, and therefore the angle, which angle here? PLO is going to be half the angle NLP, and similarly the angle O, PLO, PKO is going to be half the angle PKM, for exactly the same reason. The triangles OPK and OMK are going to be congruent for very similar reasons that I've just described. So they're equal to a right angle. So now if we look at the triangle KOL, I know that this angle here and this angle here adds to are equal to 1 right angle, but the angles, the sum of the angles in a triangle is 2 right angles, and therefore the angle KOL is equal to a right angle. And therefore, because the angle in a semicircle is a right angle, KL must be the diameter of some suitable semicircle, and therefore completing the circle, I get a circle with diameter KL, and which passes through the point O. Okay, so let's take a look at the challenge part to this problem, the second part, which is as follows. Prove that for different positions of point P on the arc MN, a family of circles is obtained tangent to each other at O. Okay, so first and foremost, before attempting to solve a problem, you've got to make sure that you understand the what it is that you're being asked to do. You have to understand the terms involved, so when it says, for example, a family of circles tangent to each other at O, if, for example, you don't know what this means, then there's no point in trying to solve the problem. This is the first thing. When it comes to solving any problem, you really have to have a good understanding of what the problem is specifying. What are you specifically being asked to do? And if you don't understand that, the problem is going to be basically impossible for you to solve. You might solve it by chance, but you won't necessarily realize that you've solved it. You won't necessarily understand why you solved it or anything like that. But also understanding the specific wording of the problem, the specific terms that are involved in the problem, in the statements of the problem, might actually point you in the right direction to a solution. Okay, and that's what happened for me in this particular case. I mean, it doesn't solve the problem for you, but it can point you in a very clear direction that you need to go in. So first of all, we need to know, what does it mean, different positions of point P on the arc MN. So effectively, we've got the two tangents. If you remember from the previous diagram, we've got the two tangents parallel, which intersects the circle O at M and N, which I just drew horizontally just for ease, really. And then we've got the arc of the circle MN. and P is the point of contact with this third tangent with the circle, and that can be at different positions, therefore. So we've got a point P which we can consider as being potentially at different points on that arc. What does it mean for circles to be tangent to each other? Well, if this is one circle, just like for a line to be tangent to a circle, the line will intersect the circle at a single point. Similarly, we can extend that idea to circles. How can we interpret circles being tangent to each other? We can speak of circles being tangent to each other if they touch at a single point. Now, this can happen in different ways. So we could have another circle outside here, for example, which just touches the circle at this point. That's not what's going on in this case. That is one possibility. But we've also got the possibility that the circle, the second circle is kind of on the inside of the first circle. Okay, if I drew something like this, these circles, the big circle here and this circle, are not tangent to each other. They intersect, but they're not tangent to each other. In the same way that if I drew a line like this, that is not a tangent to the circle. So we definitely need circles that touch at a single point. But now we're talking about a family of circles which are tangent to each other. And this kind of complicates things a little bit. And we've got to think a little bit harder. How could this happen? So the only way that this can happen is if the circles have different radii and all intersect at the same point. And there's, critically, it also suggests that the centers of all of these circles, the centers, the locus of the centers is on a single straight line. So it's not that the locus of the centers of the circles of different radii is kind of all higgledy-piggledy all over the place, wiggling all over the place, things like that. It's a single straight line. And this is what gave me the direction, the kind of direction that I need to go in order to solve this problem. Okay, so we've got the center of this circle here, the center of the other circle there, the center of the original circle there, and I can draw a straight, not very well, evidently, but I can draw a straight line, and all of the centers lie on that straight line. There are other possibilities. We've seen we could have a family of circles which are tangent like this to one of the circles, but these are not tangent to each other. These are not tangent to each other. So when we talk about the circles being tangent to each other, we understand that in the sense that every one is tangent to every other one in the family. Okay, and that can only happen in this way. Okay, so let's draw a diagram now of the situation. Remember, diagrams don't have to be drawn accurately or anything like that. They've just got to be sufficiently representative for them to be useful to us. And there's no saying that I have to draw a circle looking like this. I could, for example, I could represent my circle as something like this. This would be silly, in my opinion, but there's nothing stopping me from having a diagram where my circle looks something like this. The point being is that we never make inferences directly from the diagrams anyway, but as long as the diagram is useful to me and helps me solve the problem, that's the most important thing. Naturally though, if we've got a problem that involves circles, it probably would help to draw something that at least resembles a circle. But you have got a lot of flexibility and leeway when it comes to drawing diagrams. They don't need to be accurate diagrams. So we've got our parallel tangents. intersecting at M and N. This is O. Okay, so this is the arc MN. Well, in fact, we've got two arcs. We've got this one, or we've got this one. We can just take one side though. And we can do even better than that actually, because if we draw a line parallel to each of these tangents through O, we're going to get a point here, let's call it X, on the circumference of the circle. Really, we only need to consider the possible positions of P on kind of this quarter of the circle. So this arc between X and M, or between X and N, whichever we prefer, but I'm going to go for between X and M. Okay, so let's put our point P, for sake of argument, here. And we're going to get a tangent. That's going to determine a tangent. Not necessarily easy to draw. We've got K there, we've got L there. We know that from the previous part, we can draw a circle with diameter KL, which passes through O. Now, what we find here is that as P moves, if K and L are, if this line is perpendicular to the original tangents, then P is going to be here, where X is. As P moves around here, what we're going to find is that the length of the line KL is going to increase. And I'm going to show that in a second. So it's easy to see that from a diagram, because if I draw P up here, I'll draw a line that's evidently much longer than this one. But again, we don't make inferences directly from the diagram. We need to go through some suitable logical deduction to show, to substantiate our claims. So I claim that, and I'm going to prove later on, that as P moves from X to M, the length of KL will get longer and longer. So we're going to get the circles that we can draw that pass through O with diameter KL are going to be of different diameters, or different radii. They're going to be all different sizes. But remember what I said when I was talking about circles being tangent, the family of circles being tangent to each other? Their centers need to lie on a straight line. Well, I claim that the centers will all lie on this line that I've drawn. So this line from O through X and parallel to each of these tangents. I say that the center of the circles or the midpoint of KL is going to be on this line, irrespective of where P is going to be. And how can I show that? Well, one way that I can show that is to think of a perpendicular through here. So the line KL is going to meet this line O at the point, let's say A. So what I'm going to get is a diagram that looks something like this. I've got KL, KL, this is A, and I can just give these names, what can I give them? P and, no, not P, because P's already been used, R and S. Well, that angle is the same as that angle. That angle is the same as that angle. And therefore, this angle is going to be the same as this angle here. So these two triangles are going to be similar. So the triangles ARK and ASL are going to be similar triangles, but I also claim that they're going to be congruent. So how do I know that they're going to be congruent? Well, I know because this line here, O through X and through A, it bisects the line RS. So the line AR is equal in length to the line AS. So therefore the triangles ARK is congruent to the triangle ASL. Okay, and that means therefore that AK is equal in length to AL, and therefore the midpoint of KL is here at the point A. So the center of the circle that I can draw with radius KL, irrespective of the position of P, is always going to be at A, which is always on this line. Remember what I said, this family of circles that are tangent to each other all have to have their centers on the same straight line. That's what we've shown here. Okay, how do I know that the as P moves from X to M, that the radii of the circles is going to be, it's going to effectively increase. Okay, well, so if I how can I draw this? If I choose another point here, P primed, and draw another tangent in here, so I'll get L primed, I'll get K primed. So I'm going to get something that looks like this. K, L, K primed, L primed. Okay, these triangles are similar. Their point of intersection, I don't know, what shall I call it? Maybe I've used R, I've used S, let's use T, for example. So in triangles, the greater angle will subtend a greater length side. So this is a fundamental. You can find this proved in Euclid's Elements, in book 1, I think, of Euclid's Elements. So in this triangle, this angle here is greater than this angle here. Okay, so therefore the length of this side will be greater than the length of this side. So in other words, TL primed will be greater in length than TL. So we can see as P moves around further and further towards M, this will, L primed will get further and further over here, and the angle here will get smaller and smaller, and this will move further over here, for example. And what we'll find is that the line TL primed will always be longer than TL, whenever L primed is further out than L is. So therefore, since TL primed is greater than TL, and TK primed is going to be greater than TK, then TL primed plus TK primed is going to be greater than TL plus TK. So in other words, the radius of the circle on K primed, L primed is going to be greater than the radius of the circle on KL. So the upshot is that as P moves from X to M, the radius of the circle will increase. The radius of the circle that we can draw on the line segment KL will increase, and moreover, the center of each of those circles is going to be on this line, is going to be at the point A, which is going to be on this line through OX, on the same straight line, in other words, and therefore all of those circles are going to be, that we've got a family of circles, all of which pass through the point O, therefore they're all tangent to each other at the point O. So the next thing that we'd have to figure out, and I'm not going to do it in this video, is how to actually write that out as a solution, a convincing solution that's presented in a way that somebody's going to understand it. That's a separate issue. I've given the main ideas here. How to actually write it out, that's a completely separate issue that I'm not going to cover in this video, sorry. But that gives us effectively a solution to our problem.